carrying on in my group in Lyon. This is related to second harmonic generation at the nanoscale. I've put the title starting with nanoparticles, ensemble to single particle, and molecular organization of liquids at the nanoscale again. And what I'm going to do is to do the reverse. I will start with liquids and finish with nanoparticles and single particle in a way of building up the ideas on how I'm organizing this research. So the outline, there will be 3 things: fundamentals, very short to set the scene. There will be then the part on liquids, and then nanoparticles and single nanoparticles, and you will see where we are on the recent work in single nanoparticles. So second harmonic generation, one of the simplest processes in nonlinear optics. You have the annihilation of 2 red photons to generate a blue photon, where we use red photon and blue photon in our setup. So that's why I kept these colors. And you know that in generally speaking, we use second harmonic generation for a high efficiency. And therefore we use macroscopic materials. And one of the conditions that we have to solve is phase matching. That is, we need the velocity of the 2 waves, fundamental and harmonic, to be the same so that we have maximum intensity. So you see the expression. I've used the simplest non-depletion of the pump approximation. So we need to solve this equation with the maximum intensity. That is, we want delta KL to be 0, which translates into matching the optical indices at omega and 2 omega. So the delta N in the formula you see below in phase matching condition. However, if we go for nanoscale, you see that the size of the material, L, is much smaller than the wavelength. Therefore, this delta KL condition is always fulfilled. And therefore, that's okay. And therefore, what we're going to do is actually forget about phase matching. And what we're more interested in, if you look at the intensity, is the other knobs in a sense. We have the intensity, of course, but there are limits, okay? I mean, we do not want to destroy our material. Therefore, L is fixed, and therefore small, but more or less fixed. So the only knob we have at our disposal is Chi2. So what we're going to do is have a deeper insight into Chi2 at the nanoscale. And Chi2 will be, of course, the highest efficiency, but we will see that this translates into symmetry and organization at the nanoscale, and that's really what I want to show you today. So we can figure out this with simple drawings. The first case would be a macroscopic perfect nanocrystal that I've schematically put up as arrows well-oriented. In this case, we have a non-centrosymmetric material. We produce coherent SAG, and if the system is macroscopic, this is the first topic. So this also can be used for nanoscale material made of non-central symmetric material. One of the most common material, for example, is lithium niobate, and I'll give an example of that. In this case, we have the so-called coherent second harmonic generation. The response of all these tiny dipoles is a coherent superposition. If we go to the second drawing, you see it's a perfect alignment of up and down dipoles. It is fully centrosymmetric. This is perfectly centrosymmetric. Therefore, there is no SH. That's why there's no blue arrow at the bottom. There can't be any second harmonic there. And that's what we usually learn when we do macroscopic second harmonic. You can't do that in centrosymmetric material. Now we wonder what's going to happen with random materials. Random materials, are they centrosymmetric, non-centrosymmetric, and whether we can produce second harmonic, what we can learn from second harmonic. That's the main topic. One first topic one first random material is actually the topic of the current collaboration between Alejandro and myself. This is powder materials. This is a random material. You see a drawing where you see the grains, they're randomly oriented. And therefore, when you shine your light through, okay, what you can see is that as the beam waste, which is the, I don't have a pointer, but just quickly here, this is the beam waste. This is the main region of generation of the second harmonic. And you can move it through from the air into the powder. Therefore, you get your signal. So you see that this signal demonstrates that you can get second harmonic from a random material. In this case, you see that the rising edge is totally defined by the beam waste, and you control that by the numerical aperture of your focusing lens. But the decrease is due to multiple scattering, because in most cases, in your powder, you will lose your signal due to multiple scattering. Okay, that's a first material. I will not further discuss this, but this is, we have a random orientational distribution of the nonlinear dipole. Now, if we go to another type of material, this is liquids. This is also, a priori, a random assembly of tiny molecules. Just think about water. We can, at a first glance, see it as an assembly of molecules, and they're randomly oriented. But you see, you can still see the second harmonic. This has been reported in the 60s by Marker, Marker and Savage. You see actually here the second harmonic light, this big peak on the left side, and the other peaks are hyper-Raman bands that we will not discuss. And we can perform exactly the same experiment as before with the powder. We have a beam of light focused at the air-water interface. And as we move the focus from air into the water, you see that we have a rising edge. And because in the material, we do not have too much scattering because it's more transparent and homogeneous, then we have a flat second harmonic that we can collect. Actually, we do have scattering, but this is on a much longer length scale, and therefore we do not lose our material unless we go very deep into the liquid. Okay, now it seems that everything is fine. So what we're going to do now is focus our attention on the experimental setup, which is slightly different. We're going to shine light in a direction, so it will be a red beam. You see the red beam with a nice red filter, which is just to cut any unwanted second harmonic generated prior to the cell. We focus in the cell. And in all these experiments, we're going to focus on the light scattered at right angle. So you see the beam of light, the blue light, second harmonic, will always be collected on the right angle. In this case, we can plot this intensity. So we rewrite the intensity as a function of all these coefficients. And I will come back to these coefficients. You see that we have specific modulation as a function of the input polarization angle. And you have a half-wave plate there to control it. And on the second harmonic, you can either collect vertically or horizontally polarized. Okay, that's the setup. And I will come back to these numbers and parameters later on. Now, the interesting thing is that you can start by using molecules dispersed, or big molecules, organic molecules, which are very efficient for nonlinear optics. They have a high cross-section per second harmonic. You disperse them in a solution, and then you look at the second harmonic you produce, because we know that even if these molecules are dispersed, randomly oriented, because that molecule is in a liquid, they will produce second harmonic. So this has been done in the 90s, very early 90s, by the group of André Pessoens. And you see that the intensity in this case just add up as the sum of the number of molecules. So that's why you see the N is the number of molecules. You have the solvent and the molecules. But if we disregard the solvent for the moment, we just have an intensity scaling linearly with the molecules you put into the solution. And that's the graph you see for a one compound. You have this linear dependence. So with this, we can determine the first hyperpolarizability of molecules and control that perfectly. Okay, now what we're going to do is focus. Oh, great. Thank you. So what we're going to do, but I'm okay, they will not see, but I will try to point. So what we're going to do now is focus about this second harmonic polarized, as I mentioned before. So you see the theory for this type of molecules. So we fix the concentration and we play with the polarization. So the blue light is here, the blue curve is for the vertical polarization, and we rotate the input angle of polarization. And the red one is actually the flat one, which is the horizontal polarization. Horizontal polarization will be, in this case, if you remember, parallel to the direction of propagation of the fundamental beam. So this is the theory for the molecule we've just discussed, dispersed in the solution. And you see that if we do the measurement, it works pretty well. This is the theory. This is the experiment. It works pretty well. So we have some information. I'll come back to that later on, but you see that more or less everything fits. We have random material. You can generate second harmonic. It will be incoherent scattering. It's a linear dependence with the number of molecules. And we can have the polarization dependence where we can get insight into the nature and the structure of these molecules. So everything's, yes?
What's the meaning of the red line? The red dot?
The red dots, oh, that's the two polarization. We send a light like this, we collect like this, we rotate here, and we collect either like this or like this, okay? And the red is like this, the blue is like this. So is it the end of the story? So now we want to see if this works for water. The main difference before compared to the previous one is that now water molecules are very close to each other. Okay, you can calculate and you can make molecular dynamic simulations. Whereas before, I was using a solute in a solution at a micromolar range. Okay, so the molecules are very far apart. They do not see each other. And therefore, it's really a random material. Whether water is a random material, this is another story. So the hyperpolarizability, which is just the cross-section for second harmonic of a single molecule, has been computed in the past. So we thought something was really clear with water. So this is the experimental work. Remember what we're supposed to find, incoherent. We do water, so pretty good. We get the blue light, that's fine. We get the red one, which is flat. So far, so good. Except there's a big discrepancy. This one here are identical in intensity for these two angles, whereas here you see that actually the red is slightly below the blue one, okay? And the theory doesn't allow that. The theory really tells you that it should be the incoherent second harmonic. So there is something beyond into this that we need to understand. We've tried another liquid, methanol, and you see there is suspicion that also there is a problem. The blue one goes below the red one, slightly, but still, okay? So this tells us that it cannot be the end of the story, especially for water. So there is a problem. We need to understand why we have this. And this is due to the fact that actually the theory of really incoherent, that is a random material, where the dipole do not see each other, may not be correct. So how we can relate this? Well, we go back to our setup, okay? This is the second harmonic line, okay? We go back also to this curve, and I've selected just this one. You see that we have this very nice two lobes, but actually, if we make a very fine analysis of it, you can do well, it's a kind of Fourier transform of the previous cosine squared, sine, cosine squared, and so on. So if you do it's either, you call it a linearization or a Fourier transform, you will have three components. And the first two are present, and the last one is absent for incoherent second harmonic. So what we've done is we've seen this. You believe it's actually close to the incoherent case, but in fact, there is a residue, tiny four lobes that remains, that is this component is present, okay? So beyond this, the fact that the red horizontally polarized light is not at the same, at the bottom of the blue one, behind that, we also have this contribution. And this is important. And where does it come from? It comes from correlation of molecules. So why there is some correlation of molecules into this is the fact that a water molecule has a dipole. So its neighbor cannot be randomly oriented because two dipoles, they want to be à la queue leu leu in French. I don't know how you would say this in Spanish, but they would be like this, okay? So this one doesn't want to be like this, wants to be this, okay? So in the probability of orientation, there's a bias. That means a correlation. So in this random distribution, actually, there is a tiny contribution of coherence. And that's what we see through this, okay? And this is due to dipole-dipole interaction into the liquid that we can easily pick up with hyperrelay scattering or second harmonic scattering. So what we've done is to play with this. So this is neat water. And what we've done is we wanted to disrupt this correlation. So if this is due to neat water, what we're going to do is actually introduce salts. Because if I put an anion or a cation, will be the reverse, water molecule want to reorganize around the ions to solvate or to hydrate these ions. And that's what we get. That means you get this, and you see that this disappears. You know, it flattens out. But actually, there's a very intriguing thing that you may notice. The phase has changed. Here, at 0, we start with a maximum, whereas here, we have a minimum, okay? So it decreases, okay, it's smaller, but it has flipped the phase. And this is actually the control. Actually, the control is just the previous molecule, the big molecule that was working pretty well in terms of incoherent scattering. And actually, what that means is that we have seen the reorientation of water around the ions, and we can draw this type of line where actually, maybe I can just show you, you know, this parameter there, I can plot it. It goes from positive value here when this is neat water. Maybe maybe. So we go from this side, okay, to negative values this side. Actually, this is not the end of the story. We're starting to look at higher electrolyte, higher concentration electrolytes. And here it goes like this, okay? And we're still working on the theory to unravel in details this, okay? So what we see is a transition between dipole-dipole interactions to ion solvation here. And you see that the decrease in amplitude is just this amplitude and this amplitude, okay? Simple view at the theory, for example, doesn't, you know, just do this and goes to 0, whereas we see this, so we're still working on the theory to explain that, okay? So you see that with even simple systems like the liquids, there is organization and it's not fully random. We've explored many different liquids. You see liquids, water is here. Not surprisingly, acetonitrile, there's a big dipole, is just like water. Here you have the dipole and here the phase. So on this side, you have the positive phase, like water, acetonitrile, like trichloromethane is just there. Dichloromethane is close to no interaction. That means really random organization. And if you go to methanol, ethanol, and even octanol, you see that you have longer chains and they will have tendency to interact, but this would be steric interaction, very close van der Waals interaction. And therefore you switch to positive side, but with bigger numbers on this side, okay? So with liquids, you see this. Now, let's go back to our molecules, because now we know that when we do hyperrelay scattering or second harmonic scattering, I should say, for simplicity, we can pick up correlation between molecules. can we enforce correlation between molecules? So let's go back to our molecule, this one. It's perfectly organized or distributed in pure methanol. It's a good solvent for that molecule. Okay? It's this big molecule that is schematically represented there. So this is the two lobes that we've seen before. If I use a polar plot, I have a nice two-lobe figure. Okay. Now what I'm going to do is I will add water. But as add water, what I'm going to form is aggregates. I may not talk about my cells at this stage, but this is aggregates of molecules. And if I plot the response that I can expect from this structure, so if I organize these molecules like this, remember, it's a kind of enforcing interaction between molecules. What I will get is 4 lobes. And you see that now, when we go to this concentration, we have 4 lobes. So what we can pick up is the fact that now, in this mixture, the molecules is both organized as the well-dispersed molecules plus aggregates of molecules. And we can see that. And we can even quantify the ratio between the two contributions. We can do even further because this molecule is cationic. Therefore, if I put SDS, which is an anionic surfactant, I will also further enforce this aggregation structure. And you see that we can, as we increase the concentration of SDS, we go from this one, which is the one I've more or less shown previously, but we can move on to this one, where actually it's almost fully aggregated. So in this case, we can really pick up the signature of the molecules forming aggregates, but these aggregates are randomly distributed into the solution. Okay? So an application of that is obviously to go to micelles. So even though these compounds, this is TTAB, which is a cationic surfactant, or SDS, which is an anionic surfactant, these compounds have a tiny, tiny cross-section for second harmonic. We can still pick up the formation of aggregates. This is the theory with different models, but you see, as you increase the concentration, it linearly increases. This is the standard theory. But when you reach the critical micelle concentration, what happens is that you form equilibrium with micelles, and the response from a micelle is different from that of a molecule dispersed. And you can pick that. This is the experiment where you have the increase, the drop. Okay, there is noise because it's a very tiny cross-section. And here, this is for the anionic one. Okay, so you can use second harmonic scattering to pick up micelle formation. We've also had another type of system. It's just I just quickly go and give an overview. We can go to ionic liquids. An ionic liquid is formed. So we've chosen this type. There's many, but we have TFN here, the anion, and here the cation. But you see that this one is a C2, so we can change the length of it. And if we change the length of it, we should, in principle, recover what we've seen before. For liquids, there will be more interaction, like steric interaction. And that's what we see as we increase. This is C2. It's not, I can't remember. Okay, we've lengthened the chain. We have the result here for the famous parameter. You see that it goes down and then saturates as we increase the length of the cation. Therefore, we can also pick up into the solution the fact that we have an amount of interaction and therefore a small coherent contribution beyond the simple incoherent major contribution. Okay, how from there we can go and think in terms of nanoparticles. At a first glance, you would say, oh, it's totally different topic. In fact, there are interesting possibilities. First, if I use non-centrosymmetric type particles, this is lithium niobate, 45 nanometer diameter. You have a TM picture. I see the second harmonic scattered light. Okay, this is, I use 800 nanometers, so I collect the beam at scattered at 400, so that's fine. And I can plot here the concentration dependence, works very well. I can do the polarization, but this polarization, you see, okay, this is a circle. It was flat when I fully developed the graph, and here the two lobes. This is exactly what I see from a molecule. So for a non-centrosymmetric molecule, particle, small enough, then I can use the same formalism that I've used for molecules. And in this case, I can even work out the cross-section that I will call the first hyperpolarizability, and it should relate to the chi2 of the macroscopic material scaled by the volume of the particle. And that works pretty well for lithium niobate, for example, and other compounds, okay? So for non-centrosymmetric particles, okay, they will behave like molecules. Now we go to different type of particles, which are gold particles, would be the same for silver. These particles have, they're centrosymmetric in terms of the crystalline structure, and therefore we expect different things, or we may expect different things. So we've done, again, concentration dependence. That works pretty well. So just like molecules, and we can determine the first hyperpolarizability. So this up to there is exactly just like before. Except now we have to wonder, but what is really the origin? Because it's centrosymmetric. Where can we generate second harmonic from such a material? Quickly, you see that it's more complicated. And actually, if I reproduce here a particle, the bulk will be 0 because it's perfectly centrosymmetric. These materials are cubic face centered, so there will be no material. But at the surface, you see, there is a breaking of this centrosymmetry. So the response will be surface. Okay, that's fine, but this is very local. We have to take into account the surface, because you see, if I integrate this over the whole surface, and then I use a perfect sphere, it should cancel. So we will have to take care about shape. Okay, so we've discussed a whole lot of different shapes that now we can develop a synthesis for many different shapes. Okay, first thing with nanoparticles. How this relates to liquids, it's the fact that if you take a cube, for example, just to make it clear, you have 8 corners, and the 8 corners will be the siege of the second harmonic response. The face here, you see they're dark. This is a simulation. They're dark, and that means that their response is negligible compared to the corners. So what I can do, okay, my cube, and instead of considering a sphere, just like before, I will only consider 8 of these dipoles that I will fix. So it's a kind of a cube now dispersed in a solution, is an aggregate of 8 of these dipoles, and the relationship with these 8 dipoles is fixed. And then I have the dispersion. If I want to discuss a sphere, okay, I will revert to the previous model where I have all these dipoles you see here developed onto the sphere surface. Okay, so you see that it's the same way of describing those particles by saying that I can discretize the surface and therefore carry on with the same modeling. It's a bit more complicated with these particles. First, we have to take care about the size because it comes from the surface. But if I start to have bigger particles, I may think about the fact that what I see on one side of the sphere will not be the same on the other side, okay? Because there is the wavelengths and the spatial phase. So I need to take that into account. I need to remember that. So that's the first thing that we will see. And there's a second one, which is obviously plasmonic resonances. We have worked on it, but I will not discuss plasmonic resonances but you see here the dipolar resonance and the quadrupolar resonance of the surface plasmon resonance. Okay, so what's going to happen? We start with tiny spherical particles. But you see here on the TM picture, okay, they're close to spherical, but maybe not exactly perfectly spherical. And what we get with this polarization analysis, these two graphs, and this is exactly what I was observing for molecules. Therefore, a tiny particle of gold behaves just like a molecule. Yes?
I don't know if you already mentioned it, but those nanoparticles are colloidal or are supported with something?
No. They're never supported. They're supported for this TM picture, but we always consider them distributed in the solution. So colloidal solution. Yes. Okay. So what we've done now is to increase the size. So these are the 20 nanometer particles. This is 50, 80, 100, 150. Again, you see the 4 lobes developing. And that's due to the growth of the size. And that's really the fact that actually, when you shine light on this particle, this side sees a field, but the other side doesn't see exactly the same field because of the spatial phase. Therefore, you have what we call retardation, which is the spatial phase in another word. Okay, so we have to discuss now, beyond the shape, also the retardation. So to do that, I had sketched one of the parameters, and the first parameter that we're going to use is this one, where we use B minus A plus C, and we normalize to B. This coefficient is interesting because in the incoherent case that I've shown at the start of my talk on the molecules, this is perfectly equal to A plus C. That's why we had this very nice shape. And therefore, it goes to 0. So it should be 0 when it's a perfect tiny object, no retardation. If there is retardation, this equality breaks down. This is no longer 0. And actually, if it's a pure perfect sphere, it should be 1. Therefore, now we can plot as a function of size the previous results where we report this coefficient. And you see these points, experimental points. And this is a simple model where we take into account retardation. So now we have a measure of the weight of the retardation compared to the response coming from the shape. Okay, we can quantify this. So let's go back to our cubes. We see the cubes there. We have a TM pictures of the cube. We see that we can do calculation of the cubes here, and we can play again with polarization. What do we observe? Tiny cubes. We have the blue curve and the red curve again, the blue and the red for 48 nanometer, 100 nanometer. This is the edge length. Okay? And you see the zeta coefficient, and indeed, it increases as you go for larger systems. Okay? Now, can we go a bit further than just this analysis on just the size? Yes, we can. We use this coefficient now, which is the ratio of the CV and AV. Okay? So let's see what that means. If we take a cube reduced to the 8 corners, there's this way, which is the octupolar mode, where you see that any corner is on the edge related to another type, the other type of corners. Okay, or we have this one where one, you see, is related to this one. We need here non-central symmetry, otherwise there's no second harmonic. That's why there's a filled disk and an empty disk, and these ones would be different. So here the color and whether it's filled or not just means that actually we have a different value for the corner, okay, a different response for the dipoles. It's just this, the model. And you see that there is a signature for the same size, Okay, you see a different signature between those two. This one provides this one provides this. And if you remember the experiments, they were closer to this one rather than this one. Therefore, we can really say that actually the response is closer to something like this than like this. In a sense, if you think it's, there's no chance that actually all the corners will be exactly perfectly the same. So it's more probable to have a distribution of 8 different, slightly different dipole corners than perfectly identical ones. Therefore, you will be closer to this picture. And this is indeed what we see. So you see that this coefficient gives an information on the nature of the response, whereas the previous one was giving information on the weight of retardation. So if we go to this type of system, it's we can use this coefficient again, but you see it's non-centrosymmetric by shape. Sphere cubes, they were centrosymmetric. Retardation was coming very quickly. With these ones, 200 nanometer, this is the scale bar, so this is a bit smaller. There's no retardation at all. So you see that we have now we can really see that there's a competition between the size and the shape. If the shape is really non-centrosymmetric, it's difficult to see the size effect. Whereas if it's close to centrosymmetric, we will see the size effect very nicely. We have brought that further to the modeling. Okay, I will skip that. But using this, you see, we can do the zoology of this because I've shown just the cubes, the sphere, the triangles, but we can do all of them, report what we should get for the coefficients. And you see that instead of reporting D and zeta, we've reported different parameters. I've used again these two. This one is related to the D coefficient, this one to the zeta one. So we have the symmetry, the shape. Here we have retardation. Okay. So we have with these two numbers a way to fully characterize our particles in shape and size. So what we can see now, is something like this, where we have a solution of particles. We do hypercolloidal suspension. We do the analysis. We get these plots, and we can fully characterize our particle. Okay? So it's a nice way to fully characterize the particles.
Is there any influence of the concentration of the particles in the colloid?
I'm discussing up to no aggregation. If you start to see aggregation, you will see deviations, and we can discuss this, but you will see it.
But you can measure 3 particles, for example, or very.
Are you ahead of me? Because this is single particle. So we go back, we see neat water. This is what we get. Okay, this is just a measure of the intensity as a function of time. I put 31 femtomolar of 80 nanometer particles. Why this? Because I've calculated that on average, I should have 1 particle in the beam waste. That's what I get. I have the sensitivity for single particles. And I can discuss the shape of this, but I will. Okay, so we see here different concentration. We re-increase the concentration. And here there's a break in the scale to get this high concentration. So we really go from 0 to 1, 2, 3, but statistically. The statistics give you the skewness of this.
Above is for gold and below is for silver. Is there any difference in the composition, or
I did that? Okay, one should be, I don't know if this is silver and this one silver, or the reverse, gold and gold.
But
No. For what I discussed, no. The only difference would be with the surface Plasmonic resonance. There are interesting features, actually, because you've seen the plots. One is 2 lobes, when it's purely dipolar, actually. When there is the 4 lobes, it's actually a quadruple response. And actually, the surface Plasmonic resonance do not have the same wavelengths for dipole and quadruple surface plasmon. Therefore, you can favor one compared to the other. So what I've hidden is the fact that you can slightly play with this coefficient by just tuning the wavelengths. So what we've done is, first thing simple, we have used our system, we jellified the solution. So now the colloidal solution is jellified, so the particles do not move. But we know it's a low concentration. So what we do, we move the cell. So we can hide a bit and we move the cell. We get this. The dark blue, there's no particle. We're hitting the matrix. And when we hit the particle, we have this. There's a bit of noise, but still, you see that here we have the particles, and when there is the solution is there, when zone 2 is this one, when there is the particle, and here when there is this is zone 1. Okay. And this is actually the bulk solution when there's many particles. So actually, we can do the polarization on a single particle that we spotted when we displaced the cell. And what we get is what expected. We have here the pure gelatin, which is the matrix. We have here both gelatin plus single particle. We subtract the two, we get this, and this is what you would get from the ensemble measurement. So it works perfectly. Just remember, this is spheres, okay? If it were a different shape, we would need to take into account the orientation when it's fixed. Okay, okay, you can do 3D.
Sorry, the intensity was more or less the same for the
no, of course, this you see by the noise level. Here it's ensemble measurement. Okay, so then we decided, okay, we don't want to move the cell. We just want to move the particle. So what we decided to do is actually use optical trapping to trap the particle and then do the second harmonic on the trapped particle. So this is the setup. And here, for example, this is we started with 1 micron silica beads. We have the trapped particles, the other ones are moving. And you see that here there's no particle in the beam. This is the fundamental, the trapping beam, so we can see. And when there is a particle in the trap, the beam is a bit scattered. So on the detector in transmission, there is a lower level because the scattered light. So we know that here we've trapped a particle. Second harmonic, just the solvent. When the particle enters the trap, we see the second harmonic. Okay, so now we have an optical trap. Instead of moving the cell, we just trap a particle, do the second harmonic on this particle. I will skip this one for that time. We can do multiple trapping, actually, because you see we can enter 1 and 2. Okay. We can't do more. When there are 3, it's so unstable that at some point particle gets ejected. But then you get the second harmonic, no particle, 1 particle, 2 particles. So then what we can do is go back to the number dependence. That's what we've done here. And you see 0 particle, 1 particle, 2 particles. And it fits with what we should expect. That is, we recover the second, the hyperpolarizability of the particle. Okay. But then we decided that, okay, that's good, but that's not enough because the particle is trapped. I send my beam and I trap the particle, or I do not trap the particle. I do not control the trapping. What I want is to control the trapping. So I want to have the particle and decide when it's in the beam or out of the beam. So what we've done is on the this beam, the trapping beam, we put an SLM. So what we have now is an holographic tweezers, optical tweezer. So that means that, so this is the second, the system is the same. So what we can do is now move the trap. That is, we can trap a particle and place the particle in the focus of the fundamental beam or move it away. Okay, so this is live experiment. So you see the particle up, it's in the beam, and then it's removed. And actually, it's not very well. This is me taking the film, so that's why it's bad. But this is the hand of my student, and when the particle is in the beam, the yellow line goes up because the second harmonic is there. And when he removes the trap from the path of the fundamental beam, the signal drops. And he controls that by the mouse directly. Okay? So that's really now a full control of the system. And that's what we can do. Putting the particle in, out, in, out, in, out, in, out. And then we can write now 0 and 1 by ourselves. Okay, it's a full control. This one I didn't say, it's no longer the 1 micron particle, it's a 45 nanometer lithium niobate particle. So we can really fully control the second harmonic from a 45 nanometer lithium niobate particle. So that's where we are, and we will further develop and build on this. So with this, I will conclude. I hope that I've shown to you that we can do a lot with second harmonic at the nanoscale. Even though there's no phase matching, we can still do and learn a lot from the nanoscale structure. We've seen that in liquids, there is molecular correlation. And with particles, beyond the simple measurement of the hyperpolarizability, there will be a competition between symmetry and retardation, or in other words, shape and size. And we can get an origin and nature of the response of the particles. Therefore, we can do some kind of tailoring, customizing the response. We can play with this, and with single particle, we have now active position control, and therefore we can really, so it's not a simple system to write 0 and 1, but still maybe we'll find a nice application to this. So obviously I'm not alone to work on this. We have permanent staff collaborating. All these are professors, assistant professors, and researchers. These are the students. Zachary has done the optical trapping, ionic liquids, theory on liquid water, experiment on liquid water. This is more microscopy, and some further work and collaboration. You see several collaboration and still ongoing with the current, with Alejandro, former students that have built up the knowledge, and the group here with all the internships. That's why it appears bigger than, but it's nice. So feel free if you come to Lyon to make a stop and visit the group. And thank you for your attention. Thank you very much.
Thank you very much for this very nice talk. Now it's time for questions. There is one here in the public audience. I'm going to look at the Zoom questions in order to let them ask. So if there is any question here, Manuel?
Use uncrystalline nanocrystals or?
Yes. Yes, yes. It was nanocrystals, 45 nanometer, but you can tune this.
Will be the same for lithium, titanium.
Titanium, barium titanate, or yeah, of course, and titanium oxide.
Is very non-symmetric.
Yes. Yeah, of course. Yeah, what I've shown is that actually it works even for, say, silica particle. You would see, but then it would be the surface response. But for nanocrystals, yeah, any nanocrystal non-centrosymmetric would work and probably behave more or less like a molecule or a big molecule. And that's why they're very useful in microscopy as probes, because they have a very strong signal compared to a molecule. They do not bleach, so it's quite useful for molecular particle probes in biomicroscopy.
Another question, Manuel?
Yes.
Please.
Sorry for pushing with plasmonics.
No.
So, have you found any interesting results when studying the nanoparticles? I mean, for example, that changes the signal of second harmonic relation But also coupling with the formation of the plasmonic, I don't know, maybe the plasmon generates a linear polarization around, or even increasing the electric field.
I didn't get exactly what you want.
Okay, let's say, for example, the simple case that you generate a plasmon in a nanoparticle, that increase the second harmonic?
Yes, for sure. Resonances will increase the second harmonic. Yes, for sure. Yes. What I was saying to Alejandro earlier on is the fact that the particles, so the tiny particles, will have only, I mean, you know, probably for gold, let's take gold, there will be the interband transition, then the very nice surface plasmon, and then vanishing at longer wavelength. This is the surface plasmon, and it's called the dipolar surface plasmon. For gold, 520 or something. Then we have a response there. But if you get a bigger particle, the resonance broadens, especially on the blue side, and that's due to the fact that you have the quadruple surface plasmon resonance. So you see that actually the quadruple resonance is not at the same position. So if you switch from this dipolar to quadrupolar response, you see that the polarization plots will change. Okay, we have a work on this. So you can tune also this with the wavelengths. Yeah.
Thank you.
Any other question? I don't know if maybe in the audience, in the Zoom audience. Well, apparently not. So I don't see any hand raised. So well, if not, let's.
This one.
Yes,
Have you seen any influence of the trapping beam with the light that you are shining the particles? Not just in the second harmonic, just in any. Can you see like interference or something?
No, because they're different wavelengths. The trapping is 970 for the moment. We would like to go to plasmonic particles. So we either need to change the beam profile or to go to our longer wavelengths. And the CG is 800. But what we see is the fact that it could be interesting. We haven't done it, but in principle, it's a femtolaser. So it's pulsed at 80 megahertz. So somehow you should be close to trap the particle, because if it's large enough, Brownian motion will not allow it to move away. And even if you flash, you can trap it.
With the same.
With forget the trapping beam, just with the second harmonic. So maybe there's a small bias due to that. So it could be interesting to dig that up further.
Okay, if there are no other question, let's thank again Professor Brevet. Thank you very much. Thank you for everyone here.
Thank you.
Thank you.